Welcome to this short little video on how to test the center of a single sample using R. The steps are uniform throughout all hypothesis testing at this level. You ask yourself, okay, from my research hypothesis, what is the correct parametric test? And we want to use parametric tests because they're more powerful than the non-parametric tests. But parametric tests have assumptions. Once you know your parametric test, you should be able to list out all of its assumptions. And then you should be able to, and you do need to, test if your data violate those assumptions. If none of the assumptions are violated, you get to use the parametric test. If any of the assumptions are violated, you have to use the non-parametric test. So here's the situation. School zones have reduced speed limits, even when children are not present. In Stillwater, that speed is 30 miles per hour. Go over 30 miles per hour in a school zone, you can get a ticket. So, question, what is the average, and by average we mean mean, speed that cars travel in the school zone? So the research hypothesis from experience, the average speed is going to be greater than 30 miles per hour. Because this research hypothesis does not have an equals part, it's also going to be the alternative. The null hypothesis will be the opposite of the alternative. If the alternative is greater, the opposite of that will be less than or equal to. We're dealing with one sample, so our parametric test is going to be the one sample t-test. The main assumption of that is normality. And by that we mean that the data originated from a normally distributed population. To test that assumption, we use the Shapiro-Wilk test. If it passes that, if the p-value is greater than our alpha, that means it passes. That means we get to use that parametric test, the one sample t-test. If it fails, if the p-value of the Shapiro-Wilk test is less than alpha, we have to use the non-parametric test. In this case, that non-parametric test is called the Wilcoxon test. So let's begin. Let's illustrate this process with real data. Went out there and I collected the data, 4 school zones throughout Stillwater. In each, I sat around with my radar gun, scaring people, and measured 40 different speed limits, different speeds from the cars. So these 4 have nothing in common except they're the first measurements I made in each of the 4 different speed zones. So this is not paired data. They're all independent. We have single samples, so we want to draw some conclusions about the speed limits in each of those 4 zones. So let's start up R as usual. New script. First step, as usual, again, is to load your data. For no apparent reason, we'll call this dataset SZ. And it's always read.csv. And for all of our online data, it always has this as the start. And then this and the dataset name. Remembering to finish off with .csv. Run it, just make sure that it loaded. Notice there's no errors, so we're good to go. We're going to attach the dataset. And while we're at it, we're going to do a summary of it. Remember, attaching a dataset is fine as long as you're only working with one dataset in your analysis. And it does make things a little bit easier to type out. So we've got 4 school zones, Zone A, Zone B, Zone C, Zone D. We've got the sample statistics over on the left. So our first null hypothesis is that mu is less than or equal to 30 miles per hour. And we'll do that for Zone A. We have to test the normality assumption. We do that with the Shapiro-Wilk test. Zone A. P-value is 0.4742. p-value is greater than alpha. Therefore, we do not reject the null hypothesis of normality, which means we get to use the t-test on zone A. For a one-sample t-test, first slot goes the one sample of the data. Slot 2 is your hypothesized value. Here it's 30. And then the third slot goes the alternative. If you check back, the alternative was greater. 3 possible values for alternative: greater, less, and 2 dot-sided. 2 dot-sided is the not equal to version. Control R. P-value is 1.693 times 10 to the negative 8th. Because the p-value is less than alpha, we reject the null hypothesis. We conclude for zone A that the true average speed of people driving through there is indeed greater than 30 miles per hour. So the same thing for zone B. It's going to be a Shapiro test. Zone B. Because the p-value is less than alpha, we reject the null hypothesis of normality. Zone B data violates the assumption of normality. We cannot use the t-test on zone B data. So we use the Wilcoxon test, which is wilcox.test. Again, we have to specify mu, and again we specify the alternative. P-value is 2.549 times 10 to the negative 8th. Because the p-value is less than alpha, we reject the null hypothesis. Again, we conclude that the average speed through zone B is greater than 30 miles per hour. Notice we've got some warning messages here. I give you full permission to ignore those. We'll discuss in class what they mean. Third zone is zone C. Again, we'd like to use the one sample t-test. Assumption is normality. To test that, we'll use the Shapiro-Wilk test. Zone C, the p-value is 0.06944 because p is greater than alpha. We failed to reject the null hypothesis of normality. The data pass this test. Therefore, we get to use the t-test. Again, mu is 30. Alternative is greater. P-value, again, less than alpha. This t-test is our primary test. It's testing the original research null hypothesis. P-value is less than alpha. We reject the original null hypothesis. Conclude that mu is indeed greater than 30. While we're at it, let's go ahead and do zone D. Again, we would like to use the one sample t-test. As a parametric test, it is more powerful than the non-parametric alternatives. The assumption of the parametric test is normality. To test normality, we will use the Shapiro-Wilk test. Zone D speeds fail this assumption test, so we must use the Wilcoxon test. What did I do wrong? Yes, I have to add in mu equals 30 and the alternative. When I did not include the mu equals 30 in the alternative, what the Wilcoxon test was testing was whether or not the mean of zone D was equal to 0. If you don't specify a mu, the default is 0. If you don't specify an alternative, the default is not equal to or 2 dot-sided. That's important. And now we run the correct Wilcoxon test. P-value is 1.768 times 10 to the negative 8th. Because p is less than alpha, we reject the null hypothesis, conclude that the average speed through zone D is greater than 30 miles per hour. Okay, so what we did is we tested whether or not the means were less than or equal to 30. That's only half of the question, really. Something that is more interesting is, okay, we know that it's greater than 30. We've concluded that in all three, but what is it? Can we get a confidence interval on those average speeds? So let's do that next. To get the confidence interval, you do it without the mu and without the alternative. The mu and the alternative always relate to the null hypothesis. It's about testing a hypothesis. If we want a confidence interval, we're not doing any testing. We just want to learn more about mu. T-test, zone A, and conf.int equals true. For t-test, conf.int equals true is the default. So you can include it or leave it out for the t-test, it doesn't matter. We'll run that. We pay attention to the 95% confidence interval that it gives us. From this, we conclude that the true average speed going through zone A is between, we're 95% confident that it is, between 31.87 and 33.43 miles per hour. So even though we were able to conclude that it was higher than 30, we're 95% confident that it's not really that much higher than 30. I mean, the average speed is between 31.8 and 33.4. It's breaking the law, but I'm not really sure that cops would pull you over for breaking the law by 3 miles per hour. They could. For zone B, we'll do the same thing. Again, we don't need to include the mu. We don't need to include the alternative because for confidence intervals, we're not testing a hypothesis. We're just learning about mu from the data. So all we have to do is give it the data. Now note that in the t-test, conf.int equals true is the default. In the Wilcoxon test, conf.int equals true is not the default. So you actually have to specify conf.int. For zone B, we're 95% confident that the true average speed through the zone is between 33.5 and 34 miles per hour. Again, it's greater than 30 miles per hour. These people are breaking the law on average, but it's not that much. It's only between 3.5 and 4 miles per hour. Zone C, I'm not going to include the conf.int equals true. Still gives me the confidence interval, because for the t-test in our confidence interval is the default. We're 95% confident that the true average speed through zone C is between 32.19 and 33.81 miles per hour. Again, violating the law on average, but not by much. And finally, zone D. Again, for the Wilcox test, you must include conf.int equals true. Otherwise, R will not give you a confidence interval. We're 95% confident that the average speed through zone D is between 37.5 and 40.5 miles per hour. Okay, now we're getting up to some serious speed. At 7.5 to 10.5 miles per hour over the speed limit. Pretty sure police would be setting up roadblocks, traffic stings, whatever it takes to slow that down. It's kind of interesting. Zone A, B, and C, they weren't that different. Zone D is very different. I wonder if the speed zone in Zone D has some characteristics that makes it different than the zones A, B, and C. I don't know. Now let's look at some pictures. The typical plot for this will be a box plot. Box plot of zone A. That really gets a point across. There seems to be one outlier up here. Everything else looks nice and normal. Remember, zone A did not violate the normality assumption. There's a lot of things that need to be fixed vis-a-vis the Lab 3 requirements. I'll let you do that on your own. And we can also do box plot for zone B, lots of outliers there. No wonder we found out that it violated the assumption of normality. Looks kind of weird. Got a 40-mile-an-hour person and a 28-mile-per-hour person. Zone C. No outliers, but it looks skewed to the negatively skewed. Remember, the thick bar is the median, so the distance between the median and the bottom is longer than the median to the top. Looks a little skewed, not much. Remember, zone C, the speeds did not violate the assumption of normality. Believable by looking at the box plot. And then finally, zone D. Average, or the median, is a little over 38. None of those we observed were actually going the speed limit. So it really doesn't surprise us that we were able to reject the null hypothesis that mu is less than or equal to 30. Interesting. You learn a lot by looking at the graphics. So that was the t-test. Null hypothesis is we were trying to draw conclusions about a single population mu. We want to use the one-sample t-test. It's the parametric test. It's more powerful than the non-parametric test. The assumption of the one-sample t-test is that the data come from a normally distributed population. To test that, we use the Shapiro-Wilk test. If the data pass the Shapiro-Wilk test, we'll use the one-sample t-test, the parametric test. If it doesn't, we'll have to use the non-parametric test, which in this case is the Wilcoxon test. Hopefully this was helpful. Have a good day.